In this video we're going to continue to have a look at magnetic field lines, and in particular around electric current carrying wires, as you can see by the highlighted dot points there. Before we do that though, we need to actually talk a little bit about why magnetic fields exist. And it's just to sort of make sure that you've got a bit of an understanding of how these scenarios all are able to create magnetic fields. And basically the sort of the rough and ready explanation, so the one that you need to be able to sort of relate to but not actually understand in a whole lot of detail, is that it's due to the spin of electrically charged particles. So we've got those three scenarios that we were looking at in terms of the definition of magnetic fields, and we'll just take that just a step further. Like I say, you don't really need to know any more than just this basic idea of the spin of the electrically charged particles being aligned. But to make it a little bit more meaningful, relating it to bar magnets, what that means is that all of the electrons that are orbiting their nuclei, those spins are aligned. So when we say the spin, we're literally talking about the particle itself having that sort of rotational motion, and all of those electrons, in the case of a bar magnet, are orbiting their nuclei, are doing so with their spins being aligned. So that then leads to this property of magnetic fields. There's a lot more that you can do in terms of the domains of a magnet and sort of breaking it up into smaller regions, and then looking at how magnets are actually created or formed. But we can have a quick discussion about that in class, not something that we need to go into in lots of detail. When we then get on to an electrically charged particle, so I'll deal with that one next so that we can finish with an electric current. A moving electrically charged particle is going to spin. And if we take that spin, we can then identify that as it moves, it's then also going to produce a magnetic field due to the spin of that electrically charged particle. If we then take a whole lot of electrically charged particles, such as electrons, and have them flowing in a conductor, that basically means we're going to have a whole lot of those small electrically charged particles combining, or the effects of those spins of those small charged particles, and they're all going to be spinning with the same alignment, and as a result we'll see a magnetic field produced. So if we take that a step further and look at electrically charged particles in the form of a current, what that really means, if we just sort of draw a diagram of it here, so imagine that this is a conductor with a current flowing through it. So the current we'll have here will be to the left, so current being coming out of that conductor to the left. The shape of the fields that we produce here look like this, and we'll talk about the structure in terms of the spacing of these field lines. So notice that the spacing here is not uniform, so there's a bit of a bigger spacing for that last one that I've drawn. I'll just draw a similar pattern over here as well. So we've got these field lines that couple of things about the orientation of these field lines that we need to be aware of. I'll only draw the two loops because I'm going to add something else on the right here, but ultimately the direction of these field lines is as shown here, so sort of looping up the front of the wire and then back and going down over the back of the wire itself. So that represents the magnetic field given by the letter capital B. Now the orientation of those field lines, you can consider them to be concentric circles. So concentric meaning with the same center. So they're concentric circles centered on the current. Now, in order to make sure that you can identify the correct direction here, we're going to use something that's known as the right-hand screw rule. Now there are a few right-hand rules that we're going to use in identifying the direction of magnetic fields and currents and forces and so on. So it's really important to make sure you've got the idea behind each one very clearly sort of separate. So for the right hand screw rule, we're dealing with the magnetic field around a conductor. That's the application of the right hand screw rule. So magnetic field around a current, and incidentally it's also the magnetic field around a positive electrically charged object, or positive moving electrically charged object, a charged particle. So the convention here is that we're going to use thumb to indicate the direction of the current. And when we talk current here, we're talking conventional current. So we know that it's actually electrons that move, but when we're dealing with any current in any sort of electricity, we treat it as though it's the positive charges that move, and that then means that we can also treat the direction of the thumb as representing the movement of positive charges. So if we're dealing with the movement of a positively charged particle, so it's the movement of the positive charge is what we're dealing with. Thumb represents that direction. Fingers then represent the direction of the field itself. Now the reason why this one's fairly easy to remember is that if you consider a current, there's only one current flowing and you only have one thumb. If you think about the magnetic field, we've got multiple field lines in this diagram, so your multiple fingers represent those multiple field lines. Now to try and make that a little bit more understandable, I'll just add a diagram here as well. So hopefully that's clear enough there, representing the direction of the thumb pointing in the direction of the current, so pointing to the left, and then you see the fingers there are meant to be sort of curling over the top of the wire in that same direction that the magnetic field lines are moving. So thumb in the direction of the current, fingers in the direction of the field. Notice here if the current was to change direction, so if the current was now going to the right, you'd have to then sort of rotate your hand over so your thumb was pointing to the right and your fingers would then curl in the opposite orientation. So that diagram shows the direction of the field in a bit of a three-dimensional nature. Sometimes drawing diagrams in 3D can be a bit tricky, so we'll also have a look at how to represent them where we can just use a two-dimensional diagram instead. So in a 2D diagram we've got a convention that we'll use, and this will apply in all of the scenarios that we use from this point forward. The convention that we're going to see here is if we use a dot, that means that whatever it is, whether it's the magnetic field or the current or even a force, that means that it's coming towards, or if we use a cross, that means that it's going away. So if we use that diagram above, we can instead represent it in this manner, so the current still being directed towards the left. We saw that the magnetic field sort of came up the front and over the top, so that means over the top the magnetic field is going to be directed away, so we would use crosses to indicate that it's moving away. And underneath we saw that it was coming towards, and so we'd use dots underneath to show that the magnetic field is coming towards you, or another way to think of it is coming out of the screen in this particular case. So that's if we were to draw it from side on. We could also draw the same diagram sort of from front on. So instead we're going to have the current now coming towards us. I should mention over here that that's the magnetic field. And if the current's coming towards us, you can again use the right hand screw rule here. So your thumb's sort of pointing directly away from the screen or directly out of the screen, and you should see that your fingers then would curl in an anti-clockwise direction. And as we know, they're concentric circles, so we'd have to draw those circles with the same center, and again the spacing here showing that the field is not uniform. And I'll just draw some arrows on here to indicate the directions as required. So that would represent the same scenario but seen from a different perspective. Now, we've mentioned the magnetic field strength here a couple of times in terms of the diagrams that we're drawing. There are two things that we need to be aware of about the magnetic field strength around a current, and there are two quantities that we need to relate to. So just jotting this first bit down. So around an electric current, the first thing is that it's proportional to the current. So if we've got a greater current, that means we've got more charged particles that are moving along. The more charged particles we have, with all of their spins aligned, we're going to see a stronger magnetic field. So directly proportional to the current, and hopefully you can identify from the diagrams we've been drawing, it's going to be inversely proportional to the distance from the conductor. And because we're dealing with circles, the distance here is basically going to be a radius. So the letter that we use is the letter R, and that means that we've got this scenario. We've got that B is proportional to I and B is proportional to 1 on R. Now if we combine those two into an equation, the equation that we get has a constant of proportionality, and it's a little bit of a tricky one. So that constant of proportionality is going to be mu naught over 2 pi. I'll talk about what that is in a second, and then current will be on the top of that and the distance will be on the bottom. That's in the data booklet, that equation, so that's the magnetic field strength around a current carrying conductor. And finally, just to notate what each of those variables are, as we usually do. So B is the magnetic field strength in Teslas, and I is the current in amps, R is the distance or the radius, either of the two. Doesn't really matter which way you think of that. In the end, a radius is a distance anyway. That's measured in meters. 2 pi is just a constant, as we already know. And the last value in that equation then is mu naught. Now if you cast your mind back to electric fields, we had a quantity that was known as the permittivity of free space. This value of mu naught is the permeability of free space. So where in electric fields the permittivity was about how easy it is to set up an electric field in a given region, permeability is how easy it is to set up a magnetic field. It has a particular value, and that value is 4 pi by 10 to the negative 7. The units are Teslas per amp meters. So that basically means that if we go through and do that calculation per amp, and the meters will cancel with the current and the distance, and we'll be left with Teslas. Now that value is given in the data booklet, so it's not one that you have to memorize. It's just one that you need to be able to substitute into that equation and another subsequent equation that we'll have a look at in the next video.